Hey everybody, it's Mr. Francis, and this is a quick review for Chapter 5. Chapter 5, Chapter 11 now, we are going to, or Chapter 12, we're going to focus on the physical states, solids, liquids, and gases. Chapter 5 focuses primarily or solely on the gaseous state. And we know characteristics of gases, again, an infinite volume, an infinite shape that they can occupy. And this is a great table, various gases, and some of their physical properties. Okay, so as you go through this chapter, I want you to focus on two areas. One, the gas laws. These are going to be calculations that we do for the different variables. This is going to occupy the first part of this chapter. And when we talk about the variables, we're going to be looking at pressure, volume, temperature, and moles of gas. And then the kinetic theory of an ideal gas. And this kinetic theory basically tells us this is how a substance behaves when it's in the gaseous state. Okay, so we're going to start with the gas laws. And as I mentioned, these are going to be calculations involving these four variables: volume, temperature, moles of gas, and pressure. What's going to be important for these gas laws as you do the calculations is pay attention to the units. Volume is going to be obvious. Temperature, anytime we're working with temperature in the gas laws, we are working in the Kelvin scale. Pressure, we've got a number of units that we're going to see. The SI unit is the Pascal. And you can see the definition here of the Pascal itself. In the next two slides, we're going to look at, one, how we can measure it. The very first barometer, as you can see, was built and put together in 1643, and very simple. And this is a barometer that's no different than if you watch weather forecasts, and they talk about barometric pressure and weather movements, and that's the same thing. This is going to be a very important table, and this is one that I'm going to want you to refer to because this gives you relationships between the different pressure units. The most common one that we're going to see is atmosphere, and you can see the relationship here between atmosphere and pascals and kilopascals. But they'll also see measurements between millimeters of mercury and torr, and then also the bar, what we call bar. So this is a table that I want you to refer to. Okay, as we look at the gas laws, I want you to note two things. One, we always want to be able to identify what variables are being measured, okay? And they're going to tell you that in the problem. Because once you're able to identify what variables are being used, you're going to know what gas law to focus on. The very first one, Boyles Law, pressure and volume. And that's the only thing that ties into it. In fact, our lab for this chapter, you're going to be working on a Boyles Law experiment. The relationship between Boyles Law, as you can see here, volume is inversely proportional to pressure. The key to this law, temperature stays constant. So the relationship down here, basically we're looking at two physical states, the initial state, the final state. You're going to be, in a calculation, you're going to be given the initial states, you're going to be given one of the final states. Just rearrange the equation to solve for what's missing. And you can see some of the graphical evidence here. And you look at this example. One of the things I recommend, always write out the variables, the information that's given to you in the problem, and then always make sure that the units are consistent. So pressure here, hey, both of these are in kilopascals, that's great. Volume, cubic decimeters, okay. And again, we're going to rearrange the equation to solve for final volume. And again, we just plug it in. And here's why it's important to keep the units constant. We want the units to cancel out. And then we've got our units left for our volume. Boyles' law looked at the relationship between volume and pressure. Charles's law looks at the relationship between temperature and volume. And this is one that you're actually pretty familiar with in that, in this case, hey, they took a balloon, put it in liquid nitrogen, the volume of the balloon shrinks, you allow it to warm up, the volume increases. And you can see here, again, here's a graph representing volume and temperature. And again, the relationship, what's key here? It's at a constant pressure. And you see this relationship now. And again, the same thing. You're going to be given the initial conditions. You're solving for one of the final conditions. Again, a key here, temperature, make sure it is in Kelvin. Convert from Celsius to Kelvin. And again, they don't have an example, but it's the same thing that you would see with Boyles Law. The combined gas law actually combines it, as the name gives it away. You combine Boyles and Charles's gas law. And again, you're given all the initial conditions. You're going to be given 2 of the final conditions. Just solve for the remaining one. Again, temperature going to be in Kelvin with that. As you look at this example, again, note, we've got our volume, temperature, pressure, temperature, pressure. Again, note what they're doing with temperature. We're converting it to Kelvin, so we add that 273. We write out all our variables, and look at how we're rearranging this equation. And again, the importance of the units being consistent. They cancel out, and we find our volume. Avogadro's law, now we introduce moles. And it's a relationship between volumes and mole and number of molecules. And here's the key. We're looking for what we call a molar volume. And at these conditions, 0 degrees Celsius, 1 atmosphere, the molar volume, 22.4 liters per mole. And that's regardless of what gas that you're working with. The ideal gas law is the one relationship where all 4 variables are included. Unlike the other 3 laws, we only have single conditions. We introduce this constant that we call R. You see the various values for them in the units. This first value, this 0.082058, this is going to be the most commonly used value for R in our calculations. And again, with the problems, you've got, they're going to be given all the information, so you just solve for what you're looking for. The N here, let me go back real quick. Pressure, volume, temperature, ideal gas, or the gas constant. N, that is the number of moles. So you will have to do conversions from grams to moles. And again, you look at, hey, we're writing out all our variables. We rearrange the equation to solve for N. Look at what we plug in. And here's the key to that constant is those units. Look at the units that cancel out. We're left in moles. And we can use the molar mass to convert from moles to grams. There is one more law that we look at, what we call Dalton's Law of partial pressure. And now this is looking at a mixture of gases. And one of the things that Dalton found with a mixture of gases is, it doesn't matter that mixture. The total pressure of a system is the sum of each of the pressures of each of the gases in that mixture. So if you think about the air in a room, it's the total pressure of the air in the room is equal to the pressure of the nitrogen plus the pressure of the oxygen, the pressure of the hydrogen, the pressure of the water, and all the pressures of each and every one of the gases that we have in there. So this equation, hey, we're just going to add everything up with the total pressures. The key here, make sure that again the units for each of your pressure additions are constant. Sometimes when we look at a mixture of gases, we look at the mole fraction that gives us an idea about the makeup of a gas. So they're looking here, solving for the pressure of nitrogen and then the mole fraction and mole percent. And look what they're solving here. They give us a gram amount, so we convert that to moles. We do that because, again, our ideal gas law, PV equals nRT. We need moles of nitrogen. We solve for this. We're solving, so this 0.8087 atmospheres, the 673 millimeters of mercury, that's the pressure of the nitrogen in this mixture. Again, go back to table 5.1 or 5.2 to see this relationship between atmospheres and millimeters of mercury. Again, you can see the units that cancel out. And then the mole fraction, the 786 millimeters of mercury was given in a problem, and you get that percentage there. And mole fraction is just that, it's a fraction. I'm not going to talk too much about collecting gas over the water, but one of the things that you see for water, hey, that pressure increases as your temperature increases. The last part of this chapter looks at how a gas behaves, when a substance behaves, when it's in the gaseous state. And there were a number of studies, but this kinetic molecular theory does tie in a little bit to kinetic energy. But each of these postulates Each of these components of this theory dictate how a substance is going to act and how we're going to see it. Very straightforward. There's not a whole lot of surprise to this. And what we do as we continue on, we're going to look at properties based on this postulate, James Maxwell and speeds of gas molecules. And this is the important statement. The majority of the gas molecules at any temperature have the same average molecular speed. And you can actually see that in his curves here. The idea of diffusion, think about how aromas fill a room. Same idea with this property. The gas movement is not straight. It's constantly moving and zigzagging. Diffusion is a wide open area. Effusion, the key here, small hole. Okay, the gas is moving through a small hole to solve this. So here's a balloon and how a balloon loses its shape once there's a small pinhole in that. Ideal gases are at conditions that we're at right now. Real gases, higher pressures, higher temperatures. How does a gas act at those conditions? And that's what a man by the name of Johann van der Waals studied. And you can see one of the things that we looked at, hey, we got to take into consideration at higher pressures, the volume of the gas molecules come into play. At higher pressures, intermolecular forces come into play. And van der Waals adapted the ideal gas law equation to take into account the effect of gas volume and the effect of attraction between molecules. And again, you've got these constants that you can plug in, and you can do the calculations. A lot of the great things about the gas laws is they are plug and chug. Pay attention to the units, pay attention to the variables as you're going through this. Okay, if you have any questions, feel free to give me, shoot an email to me. I'll get a hold of you. Continue working. You guys are doing great. I know it's tough, and I will talk to you soon.